Today, equilibria topic. Let's start by looking at some reactions that are not reversible. So many reactions are not reversible. The two famous ones I want to talk about are copper here, and hydrochloric acid. As you should know, copper is not reactive enough to react with hydrochloric acid. So if I show you, there's the acid, there's the copper. Zilch, nothing happens. There's no reaction whatsoever. No reaction. The copper does not react with hydrochloric acid. So what percentage reaction happens? 0%. In contrast, I've got acid and magnesium ribbon. The same thing with magnesium ribbon will, as you've probably done in the past, if I take one of these pieces and drop it in, you can see all that bubbling, all that effervescence, hydrogen gas is coming off, salt is being made, and that reaction will carry on and on and on until either the magnesium has all reacted away or the acid has all reacted away. That's that one. Magnesium plus hydrochloric acid makes magnesium chloride and hydrogen gas, and that will go on and on and on and on and on and on. And how much product is made? Well, as much as is possible. The reaction will not stop until the reaction is finished. So we can talk about that yield is 100%. So that gives you 100% yield. The copper gives you 0% yield. We say this is a reaction, the copper reaction is a reaction that doesn't happen. This reaction, the magnesium reaction, is a reaction that goes to completion. Now, you need to understand that not all reactions will fall in these two categories. So, obviously, there are lots of reactions that don't react, and there are lots of reactions that go to completion. However, there are many reactions that are in between, and they're the ones we're going to discuss today. And they are what we call reversible reactions. So, these are not reversible reactions. Let's try and think about some reversible reactions. I was thinking about what experience you had, and I think I'd like to draw your attention to the experience you should have from the topic normally done in year 10 on strong and weak acids. Now here, strong acids, you should have learnt in the acids topic, are acids that turn into ions, and they turn into ions completely when they're dissolved in water. And the famous example of that is hydrochloric acid. Hydrochloric acid, that's made by taking hydrogen chloride gas and dissolving it in water. Hydrogen chloride gas dissolving in water, and that bottle has got those ions and those ions completely. Again, that is a reaction that goes completely. It's not a reversible reaction. In contrast, we introduced you to some weak acids, and the most famous weak acid you've come across is ethanoic acid, that one. Now, to make ethanoic acid, which is vinegar, you take pure vinegar, which is a liquid, pure vinegar liquid, add it to loads of water, and then what you find is that you make these two ions, the ethanoate ion and the hydrogen ion, but you don't make them completely. This is not a complete reaction. It's a reaction that happens partially, and we taught you in the acids topic that weak acids partially turn into ions when dissolved in water. Well, that is an example of a reversible reaction. And reversible reactions we show with a double-sided arrow like that. So you've got to learn to use that kind of arrow for reversible reactions. Reversible reactions are the reactions that are in between the copper no reaction and the magnesium complete reaction models that we have. Reversible reactions are in between. Their yields are definitely more than 0, and their yields are definitely less than 100%. In the case of vinegar, typically we have about 1% yield, typically. And for this one, it is 100% yield. Now, yield is a way of expressing how much of the reactants turn into products. If you get the maximum amount possible, then that's 100%. If you get none, that's 0%. Now, 1% means if you start with 100 million ethanoic acid molecules to begin with and throw them into water, 1% of them, if you start with 100 million, 1 million of them will turn into these ions. 99 million will stay like that. And you can't get more than that when you're doing this unless you change the conditions or throw more acid in, etc. And we need to talk about how we can influence the percentage yield by doing things like changing the temperature, changing the pressure, changing the concentration of the chemicals that we've got. So that knowledge, those 3 reactions, copper not reacting, magnesium reacting fully, and the idea of a weak acids, is knowledge that hopefully you've got already, and you're going to tackle this topic with that kind of knowledge that is embedded in your mind. So let's see if we can take you further and explain what are reversible reactions properly to you. Well, similar to the weak acid, the example when I was writing the PowerPoint, the example came to my head was one of ammonia. Now, ammonia is your example. It's the example you should use for a weak alkali, ammonia solution. How do you make it? You take ammonia gas. I'll get my pointer. Take ammonia gas, put it with water, dissolve the ammonia gas in water, dissolves very well. The fountain experiment is based on the fact it dissolves very well. Ammonia gas in water will dissolve and give you ammonium hydroxide solution. An ammonium hydroxide solution is ammonium ions and hydroxide ions in water, but only 1% of the ammonia gas turns into these ions as shown by that equation. That is another one of these reversible reactions, similar to my weak acid example of ethanoic acid being a weak acid. That both of them turn into ions partially, and it's a very low percentage, like 1%, and we show them by using that double-sided arrow, which is representative of a reversible reaction. So their reactions you should know. But what's the definition? I want you to learn this definition. Definition of a reversible reaction. Well, the problem I have is that when pupils answer questions on exam papers, they write, they are reactions that can go both ways. I'm not entirely sure I know what that means. Both ways? What do you mean? What are you going on about? So I don't want you to write that. It's a bit ambiguous. In your heads you might think, oh yeah, a reaction can go forwards and backwards, and that's what I mean by both ways. But you need to say that. So what I would like you to learn is I'd like you to learn when reactants react. When reactants react and make your products, at the same time, if the products can react together to make for you the reactants again, then those reactants are reversible reactions. Sorry, those reactions are reversible reactions. Basically, just that red script. The red script on the PowerPoint, learn that. That's your definition. And what that brings clearly into the thinking is that the forward reaction has to happen, and at the same time the backward reaction has to happen. And I'm often doing this in class. It's going that way and it's going that way at the same time. And that's a key point. These things happen at the same time. You cannot get all of the left-hand side reactants to make your products. If you were to start with products, you cannot get all of the products to make reactants. Definitely, there will be a position of the reversible reaction which will give a yield. The yield will definitely be more than 0, less than 100. Okay, let's move on. Learn that. Let's look at reversible reactions more closely. Now, I could pick lots of examples, but what I find quite powerful as a teaching technique is to talk in general terms, and then I can apply the ideas I developed in general discussions to specific reactions that you know happen and you want to discuss. So in general terms, look, if chemical A reacts with chemical B, reactants, and they react and make chemicals C and D, C and D are the products, then as A and B react to make C and D, then when you've got some C and D, the C and D will react together. Those chemicals, the products, will react together and make the reactants for you. And the forward reaction, if you've got A and B present, will be going on. At the same time, if you've got C and D, the backward reaction will be going on. And they'll be going on at the same time. That's what makes them reversible reactions. That's what I want to talk about. Now, this next section, my discussion, is crucial to understanding equilibria. So I want you to start by thinking that we've got just A and B. Now, I've got nothing in these test tubes. I'm just going to wave them around just because I like talking with my hands. Imagine you've got A in their chemical, B in their chemical, and you add A and B together. First, you have to mix them, and then collisions will start to happen. Remember all the rates topic. There's collisions going on, and some of the collisions are effective, productive, successful collisions, some are not, etc. So that all the collisions start to happen, and some C and D is made. Now, when you make some C and D is made, then, and only then, can C and D particles start colliding with each other. And if you have successful, productive collisions, then C and D, when they collide together, may make for you A and B back again. And that's what we mean. Now let's talk about rates of reaction. Initially, when you start, that forward rate of reaction, the forward rate of reaction is 0. Sorry, I said that wrong. It's not the forward one that's 0, it's the backward one that's 0. Initially, when you start, the backward reaction is 0 because you haven't got any C and D at the start. But you have at the start got A and B. So there is a forward reaction that will take place. And that forward reaction will have a rate. Let's call it rate forward. So when you start the reaction, rate forward is going on. rate backward is 0. After a couple of seconds, then you'll make some C and D. If C and D are made, then there's a backward reaction. So the backward reaction starts soon after the chemicals are mixed. And the backward reaction then gets faster and faster as more and more and more C and D are made. So you get more and more reaction that way. So the forward reaction starts off high and goes down. So imagine that reaction going on and on and on, but it's decreasing. It decreases because as the reaction happens, you have less and less A and B because some of it's reacting away. And then the backward reaction is 0, but it's growing. The backward reaction rate increases. It's 0 to begin with because you haven't got any C and D, but then it increases as you make more and more and more and more C and D. The rate gets more and more and more and more and more. If you can imagine the forward rate decreasing, the backward rate increasing, eventually the two rates will become the same. And then what? Well, let's have a look. RF is the rate of the forward reaction. Rate of the backward reaction is RB. At the beginning, R forward starts off high and decreases, and the rate backward starts off as 0 and increases. Eventually, there will come a time when the RF, the rate forward, is exactly balanced by the RB, the rate backward. And what that's talking about is the rate at which A and B react away is exactly balanced by the backward reaction, which is remaking A and B back again for you. So when, say, you're reacting A and B away and it's being remade at the same rate, then the concentrations of A and B will remain constant. Equally, if the forward rate and the backward rate equalize, then the product C and D, the C and D will be made at a rate that exactly balances the rate at which it's reacted away. So when C and D are being made at exactly the same rate at which they're being reacted away, then their concentrations will also remain constant. The idea is that when you have a reversible reaction, you have a forward reaction, you have a backward reaction, you give it time. And after a certain amount of time, it's different for different reactions, after a certain amount of time, the rates equalize. And when they equalize, from that moment on, the concentrations of the reactants and the concentrations of the products do not change. From that moment on, we call it dynamic equilibrium. So it takes time to establish dynamic equilibrium, but you get an equilibrium position. The reaction going on is a dynamic equilibrium reaction because there are still forward and backward reactions going on. But if I was to look at the concentration of A, B, C, and D, it would not be changing at a position called equilibrium position. Dynamic equilibrium is not like static equilibrium. Static equilibrium would be a bit like me saying, cup on a bench. Cup on a bench, stable. That's static. There's no movement going on. These reactions are said to be dynamic equilibrium because the reactions continue to happen. But the concentrations of A, B, C, and D, the quantities of A, B, C, and D, those do not change because the rate at which they're made exactly balances the rate at which they're used up. So I want you to learn. I want you to learn this definition. Again, it's in red. I want you to learn it. For a reversible reaction, where the forward and backward reactions continue to happen, yet the amounts of reactants and products remain constant, then we can say that is a dynamic equilibrium. Learn that in red. Right, let's see what my PowerPoint has in store. Right, learn that. Rate of forming chemicals is exactly balanced by rate at which they're reacting away. That's when rate forward equals rate backwards. Okay, so I want to link this now to yield. I want to link this to yield. If we talk about reactions like copper not reacting 0%, magnesium reacting away fully 100%, reversible reactions will give you a yield that's definitely more than 0 and definitely less than 100. So I just want to put it on a 0 to 100% scale. The position of equilibrium, for different reactions, the position of equilibrium is different. For example, that weak acid, the ethanoic acid vinegar, is like 1% ionized. So the position of equilibrium for that would be 1%-ish. You can move it a little by changing the conditions, etc., but it's about 1%. This one, I've kind of like picked something, put a red blob there, which is showing you a yield of like 20%. But they all will reach a position of equilibrium, and that position of equilibrium will have an associated yield percentage. And the bigger that percentage, that way, the bigger the percentage, then you've got more of the products being made. More of the forward reaction happens and makes more of the products before you reach the dynamic equilibrium, and from that on they don't change. And what if you've got a lower percentage? If you have a lower percentage, then that equilibrium position of the dynamic equilibrium is one where, if the percentage is low, you get less quantity of products made by the time you reach that position of equilibrium. Here, less products. Less products on that side, more products on that side. Less products equate to close to 0, more products equate to close to 100%. If equilibrium moves, we can change the position of equilibrium by changing conditions, and we're going to talk about that in a minute. But if the equilibrium position moves to the right, the percentage increases, therefore the yield increases. You get more products made. Now, you need to know the opposite of that. If the equilibrium position moves to the left, then that's closer notes. You're going to get lower yields, you're going to get lower yield percentages, and less of your reactants, less of your reactants will be turning into products. So what factors will affect the position of equilibrium? Well, we're going to discuss all these factors. Temperature, pressure, catalyst, adding more of a reactant. So we're going to discuss them all. They don't all affect the position, but they need a discussion with all of them. But before we do that, we have to talk about a famous Pakistani scientist, a famous French scientist called Le Chatelier. Le Chatelier, what he said was that these reversible reactions, they reach a position of equilibrium. I mean, I've been whistling on about that so far. But what he said was, if you change any conditions, then the equilibrium position will move. It will move to counteract that change in conditions that you've carried out. Let's see if I'm going to my PowerPoint. There. Le Chatelier principle. Learn this. For a reversible reaction that has reached equilibrium, the position of the equilibrium will move to counteract any change in conditions. Learn that. That's Le Chatelier's principle. You need it. And not only do you learn it, you need to understand it and to apply it. Now, I kind of think that this Le Chatelier idea rings true in the real world. You know, when the Chancellor comes around and he changes the tax on something, then fundamentally that is, for me, in my head, in my chemical head, it's changed the conditions of our society. And if he changes the tax, say on petrol, he changes the tax on petrol, he thinks he's going to get a lot more money in, and what happens is, well, people use their cars less. There is a reaction. I think it's entirely natural in the world. For me, it's rang true all my life, that when there's a big change, people react against it. That's like Le Chatelier's principle. When you change the conditions, the position of equilibrium will move left or right, and it will counteract that change that you've tried to carry out. Now, we need some examples rather than waffling on this. So I'm going to do the examples using the example of the Harbour process. The Harbour process is one of the most important processes in the world, in the sense that it's the way the world makes ammonia. That is ammonia. And the way the world makes ammonia is important because ammonia is needed to make fertilizers. And without fertilizers, we would have a lot less food in our world. So ammonia is used to make fertilizers. Ammonia, incidentally, is also used to make explosives, but I don't think that's as important. Explosives are used in quarries, etc., in demolition, etc., to supply us with rocks or to bring buildings down that are no longer needed. But the fertilizer use of ammonia is enormous for society, and I'm going to use this example, and this is always the example of choice when examiners want to test your ideas on equilibria. They will test them using the Harbour process, and the Harbour process uses nitrogen from the air, and hydrogen, which we can make by reacting methane gas. We can do reaction with methane gas and turn it into hydrogen. You don't need to know how that happens, but hydrogen gas is quite easy to get by reacting methane gas. Nitrogen gas is very easy from the air. The two are reacted to make ammonia gas, and that reaction is minus exothermic. It's an exothermic reaction. Minus 92 kilojoules per mole of energy is given out when you carry out that reaction. So when 1 mole of nitrogen, 3 moles of hydrogen react to make 2 moles of ammonia, that will give out 92 kilojoules of energy each time. Right, now my video is approaching half an hour. I'm going to stop it here and carry on the second video.